equation similar to classical wave equations, making it more familiar to physicists trained in classical mechanics. It is based on continuum mechanics, where you find that there are smooth variations of size, and these size they determine the quantum behavior. While if you look at Heisenberg's matrix mechanics, it uses abstract linear algebra with matrix multiplication, which was less familiar to physicists at the time. And even today, in our regular quantum mechanics course, we usually prefer to have teaching in terms of Schrodinger's wave mechanics. And as and when required, we make use of matrix mechanics. And the advantage of Schrodinger's approach, as I told you, is easier to understand for those familiar with classical wave equations. And we find that, in case of Schrodinger's mechanics, it has a connection to classical mechanics in the sense that from classical mechanics, we can make a natural transition through to quantum mechanics via Hamiltonian mechanics and wave theory. The correspondence principle allows wave packets to resemble classical trajectories in the limit of large quantum numbers. So in the limit, we find that these wave packets seem to follow the trajectories just like classical particles. While Heisenberg's matrix mechanics is less obviously connected to classical mechanics, since it lacks direct analogy to classical equations of motion. It relies on algebraic structures that were unfamiliar to most of the physicists at that time. So we find that Schrodinger's approach, it provides a smoother conceptual bridge between classical and quantum mechanics. Although, these two gentlemen, they had their own view of looking at nature at the most fundamental level. But when matrix mechanics was, announced, put forward by Heisenberg and Bohr, Schrodinger had his own reservations about matrix mechanics. So he was deeply critical of Heisenberg's matrix mechanics, finding it abstract, counterintuitive, and lacking a direct connection to classical physics. And therefore, since it lacked visualizable picture, he famously referred to it as a dreadful mess. This is what he had to say, especially his ideas about quantum jumps in Heisenberg's matrix mechanics. This is what Schrodinger had to say. He says that if one has to stick to this damned quantum jumping, then I regret having ever been involved in quantum theory. So Schrodinger instead preferred a continuous deterministic wave description, believing that electrons should be described as wave-like entities rather than jumping discontinuously between energy levels. So this was the point where Schrodinger had his reservations on matrix mechanics, and that's why he passed few comments on that. Now look at Heisenberg's has his own ideas about views about wave mechanics. So while Schrodinger viewed matrix mechanics as mathematical abstraction, Heisenberg has his own reservations about wave mechanics. He criticized Schrodinger's wave interpretation, arguing that it did not directly deal with observable quantities like energy levels and transition probabilities. Also, wave mechanics, while mathematically elegant, still relied on classical intuition, which was misleading in the quantum realm. So Heisenberg believed that when you look at quantum mechanics, you have to give up on your classical intuition. And that is where he had his own reservations. This is what he had to say about Schrodinger's wave mechanics. The more I think about the physical portion of Schrodinger's theory, the more repulsive I find it. What Schrodinger writes about the visualizability of his theory is probably not quite right. In other words, it's crap. So he had very strong views on wave mechanics. This is another of his quote. Schrodinger's wave mechanics offers a deceptively intuitive picture, but it obscures the essential discontinuities and indeterminacies inherent in quantum phenomena. So these were the words that were exchanged by these two giants, and so much so that Heisenberg's discomfort with the wave model, it led to tensions with Niels Bohr, because Niels Bohr was open to incorporating both particle and wave perspective. He was open to accepting the ideas of Schrodinger's wave mechanics, or Schrodinger's way of looking at things. And it was initially his friend, Heisenberg's friend, Pauli, who had worked out a hydrogen atom problem with the help of matrix mechanics. And once Schrodinger's wave mechanics was out, Pauli started working on various problems using wave mechanics. That also made Heisenberg initially. He was not happy with Pauli, that he felt that Pauli has switched over sides from an ardent supporter of matrix mechanics to wave mechanics. But ultimately, we know that both the theories, they ultimately give the same answers, and the results predicted by both are same. So to all the teachers, and Professor Ghatak is there, Joshipura sir and Deshmukh sir and other elders are there. This is my own experience about teaching Schrodinger's equation to any undergraduate student. In my opinion, one of the most unsatisfying aspects of any UG course in QM is perhaps the introduction of the Schrodinger equation. See, how do we usually introduce Schrodinger's equation in our class? Typically, we take several lectures to explain the need for QM by illustrating the new observations at the turn of 20th century, such as blackbody radiation, ultraviolet catastrophe, etc. So we first build the background, the need for quantum mechanics. And the lecture in which I am going to introduce Schrodinger equation, I usually begin, here is the Schrodinger's equation. So, we somehow, how Schrodinger got to this equation, that part seems to be somehow missing in our regular discourse. In Beser's book, for example, we start with a plane wave equation, and then you take the time derivative, and then you say, you equate it to the classical Hamiltonian, and then you make correspondence between the derivative and the operator on the right hand side. And then we say that this is here we get the Schrodinger's equation. So somehow I find that no effort is made to arrive at the Schrodinger equation in a physically meaningful way during my teaching at undergraduate course. So I hope I would like to get comments at the end of the session from experts. So with this in mind, I would like to now get to how Schrodinger arrived at his wonderful equation. So as you find, in 1925, European physics community barely had a time to comprehend the significance of matrix mechanics, and within 6 months, they had another formulation of quantum mechanics. So this new theory was presented by Schrodinger in a series of 5 papers, which appeared almost at a rate of 1 paper per month. And you'll be surprised, he completed the paper and posted it for publication before ideas of the next were fully formed. Unlike those physicists who developed matrix mechanics, Schrodinger worked virtually alone. He briefly corresponded with Professor Hermann Weyl and on mathematical problems that he encountered in arriving at his equation, but effectively he worked alone. Years later, Schrodinger acknowledged his debt to de Broglie, who introduced and first applied the notion of matter waves, and to Einstein, who in one of his papers on degenerate gas gave favorable remarks about de Broglie's work in the footnote. Typically, most of the footnotes, most of us don't read, but it was Schrodinger who caught the Einstein's footnote. It caught the eye of Schrodinger, and that triggered him to read about de Broglie's PhD thesis and his work. So, before I come to the actual derivation of Schrodinger's equation, I would first of all review the physical origins of it by putting it in its historical context. So you find that, a paradigm shift in physics occurred around 1900 because of a few experimental observations. And in an act of desperation, Planck, who wanted to get the correct fit for the blackbody radiation law, he postulated that energy which is exchanged between radiation and the walls of the cavity, this exchange takes place as a packet E is equal to h nu, or the energy exchange is directly proportional to frequency. And he postulated the idea of quanta during the exchange. So this lumpiness of quantization of energy occurred during transfer of light when it interacts with matter. Now, this was something which was taken very seriously by Einstein. And Einstein postulated that why only during interaction between radiation and matter. In fact, light itself, by its very nature, was discontinuous and is made up of quanta. So Einstein, in fact, went one step further than Planck, and he said that by very nature, light is quantized and light is particle-like. So in order to, prove as a proof of his idea, he said, why not look at photoelectric effect? And he could explain photoelectric effect with the help of a simple equation that we all know. Another important, idea which was a triggering point for Schrodinger, as I discussed earlier, was the wave-particle duality. So it was Louis de Broglie who suggested that, not only light, but in fact, classical particles such as electrons also have wave characteristics. So he extended the duality of light, dual nature of light, he extended it to matter as well. And that's how he gave the idea of matter waves. And we all know the famous equation, de Broglie's equation, which connects these two characteristics. Lambda is equal to h upon p. So where lambda represents something which is related to wave, and momentum is, of course, that of a particle. Using this, de Broglie showed that Bohr's condition for the quantization of orbital momentum in an electron revolving in an atom can be, explained by demanding that the length of the orbital path of electron has to be an integral multiple of de Broglie wavelength. So if I call it a wave, then this wave has to be, an integral multiple of its wavelength. Then and then the wave will be in phase. Then and then the wave will be complete. And he showed that Bohr's quantization of orbital momentum, which was in a way an ad hoc, introduction, was or could be explained in terms of, his idea of matter waves. So this was the background that, was known to Schrodinger, and that from this onward, he embarked on his journey, which has made him one of the greatest physicists of all times. You can say he's pantheons of physics. His name is there in the pantheons of physics. So Schrodinger studied de Broglie's thesis around autumn of 1925. And during one of the physics colloquia at ETH, Desai, in fact, asked Schrodinger to present an exposition report on de Broglie's work. So while reporting at the end of the seminar, Desai, in fact, suggested to Schrodinger to search for a wave equation governing the phase waves. So if there are waves associated with a particle, then Desai was suggesting that there has to be a wave equation which these waves must be obeying. So that, initiated Schrodinger, and that triggered his imagination. In fact, he started looking for a wave equation on the suggestion of Desai. So he sought a wave equation that was consistent with special theory of relativity. Why? Because de Broglie's theory, we all know, was developed within the framework of relativistic assumptions. So if he has to take de Broglie's wave at its face value, Schrodinger felt that his wave equation has to be consistent with special theory of relativity. So in late December 1925, Schrodinger having worked on various ideas, he ultimately arrives at a relativistic equation, which is now referred to as KG equation. We will get to that how he arrived, but ultimately, having worked on de Broglie's theory and using Einstein's idea, he was able to arrive at the relativistic equation, Klein-Gordon equation. 2 days after Christmas, it so happened that Wien, in fact, who was the editor of Annalen der Physik, the journal in which Einstein published his 5 papers of Annus Mirabilis, he asked Schrodinger to write an article on Einstein's new approach to gas theory. Einstein, in fact, Schrodinger replied that he has already 3 papers published on that subject. And now he was deeply involved in a new project. This is what Schrodinger is writing to Wien. And this is his quote: "At the moment, I'm struggling with a new atomic theory. If only I knew more mathematics." That's why he consulted Professor Weil, because at times he found he was stuck up with mathematics, and Professor Weil came to his rescue. I am very optimistic about this thing, and expect that if only I can solve it, it will be very beautiful. So he had an inkling that if he gets to this wave equation, it will be very beautiful, and it will have a great importance for physics. I think that I can specify a vibrating system that has as eigenfrequencies the hydrogen term frequencies, and in a relatively natural way, not through ad hoc assumptions. So he said that if I can correlate the vibrating systems which are classically well known with the eigenfrequencies of hydrogen atom, then he would be able to get the quantization rules without making any ad hoc assumptions. So this is what he wrote to Wien, and he had an idea of what he was about to approach. So by 26 January 1926, nearly 1 month after Christmas, he published his first paper in wave mechanics, and it was published in Annalen der Physik. But we all know that we cannot actually derive the Schrodinger equation from classical physics. It's a fundamental equation. But then the so-called derivations that we find are therefore never logically rigorous. They are justifications rather than derivations. So in my opinion, they are justifications rather than actual derivation. It is a fundamental equation in itself. So this is what most of us do. It would be reasonable simply to write down the final equation as a postulate of wave mechanics, and then to show that it gives correct results when applied to various calculations. This is usually we do when we teach quantum mechanics. So now I'll come to the first paper, and I'll try to highlight few important points which helped Schrodinger to arrive at his equation. So first paper is one of the greatest achievements of the 20th century. The title of the paper is Quantization as an Eigenvalue Problem. The second paper also has the same title. So it is part 1, part 2, you can say. And one of the most striking characteristics of this first paper is that there is almost lack of any reference to wave picture that motivated this discovery. So in his paper, he never mentions about anything about the wave picture. In his paper, he obtains the non-relativistic Schrodinger equation. He applies it to hydrogen atom, and on applying boundary conditions, solved it for psi. And he finds that the quantum conditions which were ad hocly imposed in the old quantum theory could be found as a natural outcome of the solution of the wave equation. The eigenvalues agreed with the energy spectrum of hydrogen determined by Bohr theory. And on the first paper, this is what Dirac remarked: it contains much of physics and in principle all of chemistry. So he not only obtained the equation, but he applied it to hydrogen atom, and he showed that quantization conditions can be obtained naturally. So one of the theory on which his derivation or his ideas were based on is the Hamilton-Jacobi theory. Friends, we all know that the Hamilton-Jacobi formalism, it provides an efficient mechanism to solve Hamilton's equations of motion. So in Hamilton-Jacobi theory, what we do is we make a transformation of variables. So generalized coordinates Qi, Pi are transformed to capital Qi, capital Pi. So we require a generating function to do that. And the dynamics of the system is included in the generating function itself that affects this transformation of Hamiltonian. So if you transform your generalized coordinates from old set to new set, then your old Hamiltonian will get transformed to a new Hamiltonian, and the relationship connecting them are the ones shown on the screen. So the important thing is these transformations are such that the new Hamiltonian K is equal to 0. So which implies that new coordinates and momenta are constants, because that dot product, see, Qi dot is del H by del Pi. So capital Qi dot is del K by del Pi. Now, if your K is 0, then Qi dot is 0. So the new coordinates and momenta become constant, and they can be only determined from initial conditions. So it's a very powerful tool to solve Hamilton's equations of motion, provided you have the correct generating function. Now, this theory was, well known to Schrodinger at that time. So we all know that if you take a transformation, a generating function, say F2, which is Q capital PT, then, K will be written in this particular form. And if we choose Hamilton's principal function, which we all know is also called action, as F2, then you find that on substituting instead of F2, if you substitute S, then you get the HJ equation. So this is the Hamilton-Jacobi equation, which is, which we get after carrying out transformation from old set to new set. Now, this equation can be solved, of course, or needs to be solved. And the Cartesian coordinates are connected by this, Px dot is del x by del x. And in 3 dimensions, you can extend it further. So if we solve Hamilton equation for the principal function, what we get is ds by dt as a derivative of action is nothing but the Lagrangian. So if I integrate this equation ds by dt, what I find is that S turns out to be L dt plus some constant. So I find that the action is nothing but an integral of Lagrangian, which is nothing but, difference between kinetic energy and potential energy of the system. So with this background, what Schrodinger did? So he started out with Hamilton-Jacobi equation, and he says let H be equal to the total energy of the system. And we know how S relates to P. And if I take the particle to be moving in a Coulomb field, then the energy of the particle will be given by kinetic energy plus potential energy, where U is nothing but minus E square by R. So if I take a hydrogen atom and if the particle is moving in the Coulomb field, the total energy is given by this equation number 3. Now, in the HJ formulation, if I convert, means if I write, Q and P, then the HJ equation in terms of, the Cartesian coordinates will be given by equation 4, which can also be written as del S square is equal to 2m E minus U. I'll not get into how these steps come, but it's simple mathematics. So this is where Schrodinger's genius comes into picture. What Schrodinger did, in fact, without any explanation, there is no explanation why he took S is equal to K ln psi. So for the action, he writes down S is equal to K ln psi, where K has the dimensions of action. So I can write del S by del X in terms of psi. And if I substitute it in the, this equation number 4, then I find that, the equation takes this form. So what Schrodinger did now, he replaced the quantum conditions by imposing a certain condition on the wave function psi. He says psi has to be real because quantum mechanics says that psi should be real, single valued, and 2 times continuously differentiable over the whole configuration space. And as a result, if you impose this condition, it will make the integral of the bracket of the term on the left-hand side to be extremum. So this is the key point in the entire, Schrodinger's method of arriving at his equation. So the term on the left-hand side becomes extremum. So what he makes 2 important points here. His procedure makes no reference to the wave properties of the particles discovered by de Broglie. Till now, he is not saying anything about the wave properties of the particles. He makes no reference to the quantization of energy and Planck's constant, although we know that later on K mentioned that K has the dimensions of action. So in his entire, method or procedure, he has till now not mentioned anything about de Broglie's wave properties of the particle. So if you take the extremum, if you take the integration, so the Euler-Lagrange equation for variation problem gives an equation which is this equation which we all know. If I substitute k is equal to h upon 2 pi, we get the Schrodinger equation. So see, Schrodinger, he used a trick. He used the ideas of classical mechanics to arrive at his equation. Now, this equation which he arrived, he used the method of separation of variables. He got a radial function for hydrogen atom, applied boundary conditions, found the eigenvalue, and that is what we know now. So this is the most beautiful part, or the genius of Schrodinger lies in the fact that he assumed S is equal to K ln psi. So the problem, of course, was well known to Schrodinger, and with his equation, he knew that this equation that he has is still not consistent with special theory of relativity, because the equation for total energy that he took, equation number 3 here, corresponds to that of a non-relativistic case. So he knew that equation that he got was not in consistent way, not consistent with the special theory of relativity. So if we take the relativistic case, let us see what happens. So if I, instead of half p square upon 2m plus u, I take the relativistic case. So the energy of relativistic particle is given by this equation. We all know that. So we can write now del S square becomes 1 upon c square e minus u square. And there is an additional term which comes because of the rest mass of the particle. And that is called, the term is m square c square, where m in this case is the rest mass of the particle. And once again, he carries out the same derivation, same steps, and takes the, extremum, or you take delta of the equation on the left-hand side, and he gets once again an equation. Now this equation corresponds to what is now called as Klein-Gordon equation. So when he used the energy corresponding to a relativistic particle, he got the Klein-Gordon equation. And when he used it for non-relativistic case, he got the non-relativistic Schrodinger equation. He attempted to determine the spectrum of hydrogen using this, using his theory or his equation, but his attempt, failed, because this equation or Klein-Gordon equation is valid for spin zero particle, and electron being a fermion is spin half. So he realized that when I take the relativistic case, then he finds that, the equation that he gets, the KG equation, is unable to find the energy spectrum. So that's where he abandons his efforts of finding out a relativistic wave equation. So having completed his first paper, now we move on to his second paper, which in my opinion is more intuitive presentation of wave mechanics. So he starts with a formal analogy in his second paper, and that analogy was discovered by none other than Hamilton in the 19th century, where you find that the fundamental extremum laws for geometrical optics and classical particle mechanics. What are these extremal laws? We know that Fermat's principle, the path between points A and B of a light ray in a dispersed medium with index of refraction n, we know that integration A, B, and ds is an extremum. Similarly, Maupertuis principle, it stipulates that the path between points A and B of a particle of mass m and velocity, so this is for classical mechanics, lies along the line A to B, mv ds. That integration is also a maximum. So mathematically speaking, this means that the phase phi of the light wave must vary as little as possible as it moves from one point to another. So it's a minimum, if light takes minimum path, I think I should have written it on the previous point. But anyway, if you say that Fermat's principle insists that light takes, this integration is extremum, that means the phase change when light moves from A to B has to be minimum. Now, if particle momentum varies with spatial location, in the same way that optical index of refraction does, see, this is the most important point, then the path determined by the particle coincides with the ray determined for the light wave. See, this is the crux of the entire argument. So if you look at particle classical mechanics and variation of path of the particle, and it is similar to that of optical index of refraction, then these two, particle path and the path of the ray, they coincide. So the wave psi may be described in such case in the form of psi is equal to A e raised to I phi, where A is amplitude and phi is its phase. Now, if we ignore the nature of light, treating it as particles, we can effectively, so if I take a particle view of this, then what I can say, the wavelength must be extremely small, or the frequency of these particles must be extremely high. Then and then, psi will represent the wave part of the wave matter wave. So in classical mechanics, we minimize action just as Fermat's principle minimizes phi. Now, once these two things were known to him, it was reasonable for Schrodinger to do a guess. He said that the light wave phase corresponds to action S, because Fermat's principle minimizes phi, classical mechanics minimizes action S, so somehow they must be same. So in that case, for describing mechanics, you should have the wave function psi is equal to A e raised to I upon h bar s. So where there is phi, that phi should be replaced by s, and here h bar is just to make it dimensionless. So this connection was crucial for Schrodinger to arrive at his equation. So Schrodinger used this analogy. So that's where he said he emphasized the need for wave mechanics, and he pointed out that in a medium of extremely non-uniform index of refraction. So if you have high index of refraction, a right ray is no longer well defined, and geometrical optics fails when the curvature of ray becomes large. So if index of refraction is high, geometrical optics effectively fails to because the curvature of the ray is large. Now, when similar thing happens in classical mechanics, we turn to pure wave theory, and a theory in which rays need not be assumed. So he says that under certain conditions, wave reduces to that of a particle or a path of a particle. So Schrodinger suggested this failure is fully analogous with the failure of geometrical optics. Perhaps classical mechanics is the complete analog of geometrical optics, and as such is wrong, that is not in complete agreement with reality. So as such, it is not wrong, but still it is not in complete agreement with reality. It fails whenever the radii of curvature and dimensions of the path are no longer large compared with certain wavelengths. Then it becomes a question of searching for an undulatory mechanics. And the obvious way to do that is by a wave theoretical extension of Hamilton's idea. So where, wave, idea fails, he says that we will have to have a new kind of a mechanics, which will be an extension or of Hamilton's idea, which describes, particles, but you take wave theoretical extension of Hamilton's idea. So that was a crucial suggestion which was made by Schrodinger. So coming back to the Hamiltonian theory, this is the basic, equation, Hamilton-Jacobi equation, where S, we all know, is the principal function or action. So it can be written as this. So following Hamilton, Schrodinger considered a system of S surfaces for which action is constant. See, in this case, this U comes from the potential energy. So the velocity of the system is perpendicular to S surfaces as S is equal to constant. So this is similar to, if you recall, Huygens construction. So in Huygens principle, you have a wavefront and all the particles, all the points on the wavefronts are the sources of secondary wavelets. These secondary wavelets, they propagate in the forward direction. So that's how wavefront propagates in a direction perpendicular to it. So something similar, he says, consider a system of S surfaces where the action is constant. So the velocity of the system is obviously perpendicular to these surfaces. And in time interval dt, the system moves normal distance. So normal distance will be given by this equation, where this small ds is the distance traveled. And E is ds by dt. We all know that. So this means that ds is equal to E dt upon 2m E minus u. So the velocity of S is equal to constant surface is given by V is equal to ds by dt. So it turns out to be this. And since S in the geometrical wave system plays the role of phase, V is the phase velocity, and obviously it is different from the particle velocity. So we find that Schrodinger got the value of wave or a phase velocity through this equation. Now, the next part was to construct the wave equation. So naturally, he had to provide these S phases, the S constant surfaces, with frequency. This is where he takes help of, Planck-Einstein equation, E is equal to h. So in order to give frequency to the S phases, he says, let the frequency of these S phases be equal to E upon h. Now that's why E is equal to h nu. I substitute E here, and V becomes h nu by square root of 2m h nu by u. So Schrodinger assumed that the psi waves that traveled with the S waves and their equation was the usual second order differential equation. So he says that the waves, these phases represent, they travel with the S waves, and these waves are given by the usual second order differential equation, wave equation as we know it. So 1 upon psi, so this is the wave equation where V is the velocity or the phase velocity. So he assumed that naturally psi qt can be represented as a sinusoidal function of time. So if I write it as product of one wave function, which is function of only q, then the second part will be the time dependent part. So I can write down the psi qt or the wave function as e raised to minus I 2 pi upon h bar et. So if I substitute it in the previous equation, so in the wave equation, if I substitute this value of psi, then I find that I arrive at the Schrodinger's equation. So this is how in the second paper, taking an optical analogy of classical mechanics with wave optics or electromagnetic wave theory, he connected the two and obtained his famous Schrodinger equation. Now, if you look at the relativistic case, then we know the equation for relativistic particle, and in that case, the phase velocity will be given by this, and you substitute it here in this equation, then you once again you get the Klein-Gordon equation. So, in my opinion, second paper he uses, and it is physically more appealing in the sense that he shows why he is taking these two, why he is connecting these two, and why there is a need for a separate wave equation to describe wave particle duality. So Schrodinger applied his framework once again to hydrogen atom, demonstrated and showed that the allowed energy levels, they correspond to discrete eigenvalues, and he solved the problem of hydrogen atom. So in my opinion, this approach not only offered a more intuitive understanding of atomic systems, but also showed that quantum behavior could be interpreted through a mathematical properties of wave functions and their associated eigenvalues. So something similar was done by none other than Richard Feynman. So once again, if I I'll briefly take one or two slides in describing Feynman's path integral formulation. It has its origin on the same condition which Schrodinger used. Psi is equal to e raised to I h bar SRT. So mathematically speaking, Huygens principle can be expressed as the wave function at time t2. It is integral of gxy of wave function at time t is equal to t1, where t2 is greater than t1, and the wave function gx is called kernel or the propagator, which makes wave function move. Its value changes from that at t1 to that at t2. So this propagator or idea of propagator is extremely important in quantum mechanics. And Feynman, what he did, he said that he postulated that the propagator can be expressed in terms of a sum over all the paths between 2 points, and the weight factor is nothing but this e raised to I upon h bar SRT. So the equation which Schrodinger had used, something similar was used by Feynman, and this is the Feynman propagator, which sums over all the paths with a weight factor of e raised to I upon h bar. So if you take the small step delta t, I can find out how the propagator changes over time delta t, where delta s is the increment in the action. Is the increment in the action, and that is delta s, we all know, is nothing but increment in time L dt. I put the value of L, which is p square upon 2m at t minus u. And for small t, we can approximate e raised to exponential term by this equation. So your change in the action, small change in the action, is given by this. And if you take Fourier transform of the propagator, and Feynman took the Fourier transform and showed that the limit delta t tends to 0, this once again leads to the Schrodinger equation. So this is how Feynman in fact obtains Schrodinger equation. So I'll come to the last part of my discussion. Having obtained Schrodinger equation, now the Schrodinger equation, an important question is Schrodinger equation a wave equation? So strictly speaking, it's not the wave equation in the same sense as a classical wave equation. What are the reasons a strict or a classical wave equation? It represents, say, u it represents displacement, electric field, etc. And v is the propagation velocity of the wave. So this is a typical wave equation. So this equation is second order in time, second order in space, while time-dependent Schrodinger equation is first order in time and second order in space. So in that sense, it is different. So in case of classical wave equation, you have fixed speed of propagation for all the particles is same, while in case of Schrodinger's equation, that is not getting clearly defined in the sense that these wave packets, they spread out over time due to dispersion. So the group velocity of a quantum wave packet is given by this equation, Vg is equal to d omega by dt, which are the dispersion, where omega and k are the wave number, and we get the dispersion relation omega h bar k square upon 2m. So, Schrodinger equation does not have a clearly defined propagation speed for the wave function. So this is another difference. So this dependence, in fact, this omega or the dispersion relation, what it says, different components travel at different speed, causing the wave packet to disperse. Now in classical physics, wave represents physical quantities, pressure variations, for example, in sound waves, electric and magnetic field variations in electromagnetic waves. However, here the wave function does not directly correspond to a physical reality. It can be an imaginary quantity. Instead, mod psi square gives the probability density. So this statistical interpretation differs from the classical notion of a physical wave, where the wave amplitude directly describes measurable quantities. So in this case, wave function does not correspond to directly. So I find that all these three formulations, Schrodinger's wave mechanics, Heisenberg's matrix mechanics, and Feynman's path integral formulation, they are born from different intuitions, mathematical tools, and philosophical inclinations. They converge onto the same physics, and that, in my opinion, is a testament to the elegance and universality of quantum mechanics. It's like describing a symphony through sheet music, Schrodinger, sound frequencies, Heisenberg, and the musician's movements, Feynman, all capturing the same masterpiece. This multiplicity of perspectives doesn't just make quantum mechanics richer, it deepens our appreciation of how nature allows itself to be understood in complementary waves. Isn't that profoundly beautiful? Eugene Wigner, in his famous essay, The Unreasonable Effectiveness of Mathematics in Natural Sciences, this is what he writes. The miracle of the appropriateness of the language of mathematics for the formulation of laws of physics is a wonderful gift which we neither understand nor deserve. So finally, I conclude. In his 1926 paper, which marked the birth of wave mechanics, he offers a continuous alternative to Bohr's quantum jump. So Schrodinger's wave mechanics is more visualizable as compared to, we can imagine it is, because we are trained to think classically. So it's more intuitive and appealing also. So the first paper introduced the time-dependent Schrodinger equation, solving the hydrogen atom with eigenvalue methods. His second paper generalized the framework with perturbation theory, degenerate states, eigenfunction expansions, laying the groundwork for the modern quantum mechanics. So in my opinion, the Schrodinger equation is not just a tool, it's a testament of how deeply nature hides its secrets and how beautifully they unfold when we ask the right questions. The Schrodinger equation is a single elegant equation that unifies classical physics, quantum mechanics, and the structure of atoms, giving us a mathematically rigorous yet intuitive way to describe the quantum world. So the resources that I use for my talk are an excellent book by Professor Deshmukh on quantum mechanics. Manjit Kumar's book on quantum, then Walter Moore's book, Schrodinger and his on Schrodinger's life and thought, Max Jammer's book, The Conceptual Developments of Quantum Mechanics. And these are the papers and few sources on the web which I used in preparing this talk. Finally, I'll end my today's discussion with a famous quote of Schrodinger. The task is not to see what has never been seen before, but to think what has never been thought before about what you see every day. Thank you.
Thank you, sir. Hello, sir, please go ahead.
So, the wonderful talk we had just now, I think.
Should I stop sharing or?
Yeah, you can stop sharing also. Yeah. So it was a wonderful exposition and the connections which you made, starting from the very beginning. And I think this is a masterly exposition of Schrodinger's two papers, first and the second paper. And I think one has to really, after listening to these lectures, think about that there is a very solid ground for the discovery of Schrodinger equation. And there is something more than just the axiomatic status, which sometimes we try to give to this wonderful equation which has changed the world. And I know that we have experts sitting here in our audience on quantum mechanics, Professor Ghatak and Professor Deshmukh. I believe that this lecture also makes a ground for the interview which I am going to have with Professor P.C. Deshmukh.
Yeah.
It's a very interesting part of it. In the last part, you correlated very nicely the three formulations of Schrodinger, Heisenberg, and Feynman. And after almost 100 years, when Professor Deshmukh thought of writing his book on quantum mechanics, he thought of starting with the Feynman's path integral approach. I think this is a very interesting coincidence which your talk has offered to the participants in this particular series of lectures itself. And I think it is a very interesting tutorial for the students also. And it is, it hangs in between undergraduate students and the PG students, this lecture. Because undergraduate students, you cannot really take them to such depths to which you have gone. And I can understand why Professor Ajay Khatak, when he thought of, writing his book, he also, gave Schrodinger's Nobel lecture in there. And Schrodinger Nobel lecture is a beautiful piece of saying something without using a single equation and underlining everything in terms of what you can call as the Fermat's principle. That was the most interesting aspect of that lecture also. So I think it is just great. This series is emerging like a beautiful course on the development and the history of quantum mechanics, where we are not really just putting the rigor under the carpet, but we are bringing that also out in the front. So I can only say, Professor Pruthul, thank you very much for accepting this invitation at a very short notice, but you have made the best out of it. Thank you very much.
Thank you so much, sir. Thank you.
Yeah, if there are any questions, please, you are welcome to ask. Audience, please come forward and you can ask questions. Raise your hand and I am sure you will get very good response for that.
Okay, sir, am I audible?
Yeah, you are audible. Yes, please take over.
Sir. Any comments by Professor Ghatak, sir?
Greatly enjoyed Pruthul's lecture. Really, he has gone to tremendous depth and worked out the original paper, which so happens it is quite difficult for introduced to the undergraduate students. Today now, BSc honors students, or even sometimes ordinary BSc students are introduced to this Schrodinger equation and its solution. And I find it very difficult to introduce all the concepts of this. So there is therefore and even Heisenberg's matrix mechanics. I think the best way to understand Heisenberg's matrix mechanics is to go through Dirac's book. I think that he very carefully formulates the basic principles of quantum mechanics, beautifully formulates. No one has done that better than him. Of course, Feynman has his own way of his doing that, but I think Professor Pruthul Desai has very carefully gone through all the details. But the question is how to introduce that in an undergraduate course, whether this will be this can be given as a study material or a research material for the undergraduate students, but for them to teach in the class will be very difficult. So even therefore one refrains from, I don't know, Professor Deshmukh may like to comment on that.
I think that one should not be shy of doing mathematics. The mathematics is not beyond what the students know. It is just, the knowledge about function of a variable, what happens when it varies with a parameter, how to take its derivative, and you get the first derivative and the second derivative, and there is nothing beyond the second order differential equation. And I think the mathematics is known to the students. We need not be shy of using it. I feel that we should advance it, which is the correct way of doing it. It will raise the bar more appropriately and also communicate the essential physics without any ambiguity. So I think I would like to congratulate Pruthul for showing how it can be done. And what Pruthul has done in one lecture can perhaps be taught in a course in 2 or 3 lectures. And students can be given some exercises, some problems, tutorials to catch up with the details. But I think it is very much within the reach of undergraduate students.
Thank you, sir. Deshmukh sir, are you saying something?
No, I'm done. Thank you.
Thank you. And any questions from the participants?
May I?
Yeah, yes, sir. Please.
It was a wonderful talk, Dr. Pruthul. I just want to complete it. So now we have been talking about the mathematical formalism, as Professor Ajay Ghatak also has mentioned. See, one side you have infinite dimensional vector space, other side you have finite dimensional vector space. When we mention about path integral formalism on one side, there is also formalism by Julian Swinger, who wrote in 1960 on unitary operator basis, which is on the foundation of finite dimensional quantum mechanics. And that, in some sense, generalizes, though we are writing about commutation of X and P, that is not the more general way. What one has to look at, in my opinion, is to look at the way of looking at the commutation relation. We have to look at the position and momentum representations. That was the connecting link, because Heisenberg's formalism was abstract. Unless and otherwise there is a position representation or a momentum representation, there is no view for us to look at the wave functions per se. And in that way, and I think that's where the connection comes in. When you mentioned that Schrodinger was looking at abstract, thinking Heisenberg as abstract, and Heisenberg was thinking whatever approach which Schrodinger had ambiguity in his theory. And some sort of a middle ground was made by Pauli. As Professor Ajay Ghatak mentioned, actually without taking any side, it was Paul Dirac's preface where it very clearly supports on the either side, starting from Poisson bracket actually. So he starts from there. Even there, the natural formalism of Hamilton-Jacobi comes quite naturally.
Yes.
And in that way, having worked with Professor Deshmukh also, I would also tend to align with Professor Ajay Ghatak in terms of bringing in this path integral formalism straight away into an undergraduate level. Maybe for an advanced learner, I would think as an exercise, and you can give like the way in IITs, as Professor Deshmukh mentioned, we'll give some problem sheets with some introduction actually. Like they may not know what is Poisson bracket, we'll give the introduction, then build up the thing, and then the problem solving, it was used to be there. But otherwise, giving it to a general student at the undergraduate level would be very tedious. I think that could be one of the reasons why Beiser in his approach straight away starts from psi equal to a e power I5, where he brings in e power ikx minus omega t. And from there, he derives the time independent Schrodinger equation. He didn't even talk about dependent equation actually.
No, yes, you are right. You are right, sir.
And because it's easily connectable to the, he never goes to the interaction picture at all in,
Yes.
and very even the Einstein coefficient derivation also, he was very, because it's an undergraduate level, he was very clearly exposing it.
So that was precisely my concern was that when I teach in the class, see, the way Beiser, he approaches, but suddenly I have to now say this is the Schrodinger equation. So it's like collapse of a wave function, you see. You suddenly from nowhere, you say, I connect these left-hand side and right-hand side, more operators on one side and derivative on another, and you say that this connects. So this is our momentum operator. This becomes our energy operator, and now you can write the Schrodinger's equation.
I think instead of that, we can have these probability densities classically. We have this equation which Poisson bracket also naturally arises, which has a direct analogy with IH bar dou psi by dou t in terms of rho, probability densities classically. I think that equation, if suppose one starts and giving some motivation, because people also get exposed to fluid dynamics, some part of it, continuity equation. And from there, that approach, I think, would be better than a path integral formalism straight away at the level of undergraduation, in my opinion. And it was a very good talk. And yesterday and today, it was very nice. And I'm also very happy to see some of my role model mentors, Professor Ajay Katak and Professor P.C. Deshmukh. Thank you. It was a wonderful talk.
Thank you. Thank you so much.
Thank you, sir. It is the time for next session and a much awaited session. Now we have IAPT National President Professor Ahluwalia sir interviewing Professor P.C. Deshmukh sir. This is the occasion of the recent book on quantum mechanics, formalism, methodologies and applications by Professor P.C. Deshmukh recently. Professor Ahluwalia sir will be going through the approach of the book and various other issues. Before Professor Ahluwalia sir take on, let me ask Dr. Usha Pravina, IAPT senior member from RC22, to present a brief profile of Professor P.C. Deshmukh sir. Madam, please.
Thank you, sir. Professor P.C. Deshmukh is an Indian physicist and educator renowned for his contributions to theoretical atomic physics and applied physics. He has made significant contributions to physics education, including publishing foundational classical and quantum physics textbooks. Throughout his teaching career, he has instructed courses in classical mechanics, electrodynamics, quantum mechanics, and quantum collision physics. Many of his lectures are freely accessible through NPTEL and Swayamprabha, where they benefit students and educators across India and beyond. Sir authored about 350 research publications and completed 17 PhD theses and 22 MTech, MSc, and BTech theses. Currently, he serves as the founder, convener, and mentor of the Center for Atomic, Molecular, and Optical Sciences at Technologies in Tirupati, which is a joint initiative of the Indian Institute of Technology, Tirupati, and the Indian Institute of Science Education and Research, Tirupati. Concurrently, he is a RV Chair Professor at the Center for Quantum Science and Technology, School of Computer Science and Engineering at RV University, where he guides research and educational efforts in quantum science, drawing on his vast expertise to support the center's growth and innovation. Besides, he is the Chief Technology Advisor to the Vivekananda Institute of Professional Studies, Delhi. Few of his notable positions are visiting scientist at Georgia State University, visiting scientist at University of Aarhus, Denmark, Senior Research Associate, International Center for Theoretical Physics, Italy, Head of Department of Physics, IIT Madras, Head of School of Basic Sciences and Dean Academics, IIT Mandi, visiting professor, the Western University of London, Canada, and visiting adjunct professor, Indian Institute of Science Education and Research, Tirupati, Dean Sponsored Research and Consultancy, IIT Tirupati. Sir, we are indeed honored to have you with us today. Looking forward to hear from you. Thank you, one and all.
Thank you, ma'am, for the profile. And now the stage is Professor Alwali, sir, and he will be interviewing Professor P.C. Deshmukh. Please go ahead, sir.
So thank you very much. And I am really delighted that we are having today, after Professor Pruthul's lecture, a wonderful interview which we are going to have today with Professor Deshmukh. It's a joy for me in the sense that I am now talking to Professor Deshmukh for the second time. I have also had a privilege to talk about his first book on classical mechanics, the foundations of classical mechanics to be very precise, which has been published by Cambridge University Press. And I think IEPT is fortunate that we have the blessings of our wonderful faces of the country, Professor Ghatak and Professor Deshmukh. And that is a great, I think, possibility which is there. So first of all, I would say, Professor Deshmukh, congratulations for bringing out two wonderful books, not just on the Indian scene, but on the international scene. And they have a very different kind of an approach. And as the title of this book rightly says, quantum mechanics, formalism, methodologies, and applications, it reflects a very different, I think, and I would like to know more about it, that this book very interestingly matches with both your interest as a teacher and a researcher. I think as a person who has done a lot of work in atomic physics as a researcher, and your passion for teaching this course to a very intelligent audience, I would put it like that, in IITs and ISERs. This must have really inspired you to write this book, which has got 630 pages, not small number of pages. And I think when I first opened this book, and then I saw that at what level it is operating, I was always wondering I should sit down with Mr. Deshmukh and ask him that, can you share your experience of teaching quantum mechanics at prestigious institutes, and then, thinking and working for such a wonderful work, which is very, very taxing. It is not a very small work which you have done. So kindly share with us your experiences of teaching and how you incorporated your research efforts also into the book when you were writing about it.
Namaste. Good evening, everybody. Thank you very much, Professor Ahluwalia, Dr. Madhusudan, IIPT. I think you have been very generous in allowing me to come and talk about my book. It has basically grown out of the courses I have taught primarily at IIT Madras. Yes, I have taught at some of the other institutions also. But primarily, I served the IIT Madras for more than 3 decades, where most of my courses were developed. Of course, there are great books on quantum mechanics. There is Dirac, there is Landau and Lifshitz, Sakurai. On the relativistic platform, there is Bjorken and Drell, Betty and Salpeter, and Betty and Jacques, and great books. And as you rightly observed, the opportunity to teach at IIT played a big role in developing the books, the two books which I have written. The big thing about this opportunity is that almost every semester I taught two courses. One undergraduate course for BTech students, which would be on mechanics or electrodynamics, very basic mechanics, Newtonian physics, Maxwell's theory, and an MSc course, which would be around quantum mechanics, either QM1 or QM2, or there would be a course on atomic and molecular physics. I also introduced an elective, which is theory of atomic collisions and spectroscopy, which was, again, you could even call it as QM3. So they are all these courses centered around quantum mechanics. And the opportunity to teach both at undergraduate level and the master's level. And the MSc courses were also attended by some PhD students. They have mandatory coursework. I had my own PhD students who took some of these courses. Some of them even served as TAs, which was a great help. And the courses have basically evolved out of this opportunity. So I'm very grateful to the institutions where I could teach, number one. And second, to both my MSc students and undergraduate students. And most of all, my PhD students who served as, they helped me prepare the problem sheets, tutorials, which is a very integral part of any teaching effort. I think what enabled me to raise the level of the course, both undergraduate as well as the MSc courses, was to give weekly homework problems. And we sort of encourage the students to take help from each other, to consult senior students, to consult anybody. I always thought, I never worried that, okay, they're going to copy from each other, because I took the viewpoint that, okay, if they can learn from me, why not from each other? So it was good. And there is a lot of material which I did not have the time to do in the classroom, which they studied on their own and learned it even better. And I'm very grateful to my TAs who helped me prepare these problem sets. I think the students also benefited a lot, because many students who have taken these courses went abroad to do their PhD. And some of them even managed to get waivers on some courses because they had already done that material at IIT Madras. So I think what enabled me to bring out these books was the opportunity to teach at IIT Madras, and the support I got from the students community in the institution, both undergraduate as well as MSc students and PhD students, all of them.
Thank you. I think it's very interesting view which you have really given us about your teaching of these courses and how these have resulted in the books which you have written. And I think there is a commonality between what you are saying and what Professor Ghatak was also saying yesterday. I think that's great.
Absolutely, yes.
But there is one thing which immediately, comes to my mind is that when one thinks of writing a book on quantum mechanics, coming directly to Feynman's path integral approach is a very daring kind of a step, I would say. And though, if you look at what Schrodinger was talking about, he was also talking about Fermat's principle. when you look at what Feynman was talking about when he was introducing path integral approach, he was also somehow talking about the same kind of an approach, and that what kind of a path the particle is going to take. Schrodinger, in his Nobel lecture, also concentrated almost on that itself. Beautiful diagrams talking about Fermat's principle and all those things. So I was also wondering about one thing, and that was that maybe you are seeing some very interesting developments happening in quantum mechanics at the moment. Maybe the training of the students with this formulation of Feynman may better prepare them for the kind of things which are happening under quantum revolution 2.0. Please enlighten us about that how this kind of an approach is definitely going to benefit students.
Yeah, it's much easier to comment on this after Pruthul's excellent talk, because he already elucidated so beautifully how the path integral approach really enables you to connect quantum mechanics with Hamilton-Jacobi theory. In fact, it was Dirac's idea, which Feynman developed further. So, I think the historical development of these ideas was not the focus of my effort. My attempt was to build a heuristic appreciation of these methods and their applications to do real problems in atomic physics and condensed matter physics and other areas of applications of quantum mechanics. Toward that end, I think the Dirac-Feynman approach is extremely powerful, and it brings out the essence of quantum mechanics in a very big way. One of the things which I think impressed me very much is a YouTube talk by Feynman, which I'm sure almost all of you would have heard, in which Feynman points out that the Young's double slit experiment contains most of the essence of quantum theory. The Feynman's path integral approach highlights this, because you can have two alternative paths, or three, or four, or multiple alternative paths. You can have multiple slits. You can have a scatterer in the apparatus, which can send the particle or wave or whatever you want to call it. I call it as FP, as Feynman particle. That this can be scattered away to anywhere else in the universe, which can again get rescattered and come back and eventually reach the detector. And what nature does is it allows you, it not only allows, I must say, it requires you to consider all of these possibilities, because observations then require for their interpretation and interference between these alternative paths. So whenever there is, whenever a system has got access to multiple paths, nature requires you to sum over all the probability amplitudes, which is what Feynman path integral approach does. And I think this contains the essence of quantum mechanics, which is what you see in the Young's double slit experiment. You cannot comprehend either a particle or a wave going through one or the other. What makes it even more interesting is that if you make an effort to spy on which way the particle would have gone, like in the which way experiments, which also I have discussed in my book, then the interference is lost. So the access to alternatives requires the superposition principle, which I believe is fundamental to quantum mechanics. And I think the Feynman path integral approach highlights it. Now, it is introduced early in a certain sense, but only relative to how most of us have undergone our own education system. I think today's students are ready for it because it does not involve any big idea. It requires an ansatz. But given the ansatz, the development of the method, it does not require any advanced tools. And ansatz is something that one cannot escape from if you're dealing with quantum theory. You need to begin with a certain ansatz. You need to come to terms with the fact that, okay, you cannot understand nature on the basis of what you believe is your physical experience. You have to go beyond it. And you can test this ansatz. And as we all know, there is no exception found for the rules of quantum mechanics. It has lasted 100 years in a certain sense. I think quantum mechanics is now beginning to become classical. It is no longer, new. 100 years is not a short period. If you compare its lifespan with Hamilton-Jacobi theory or even Galileo Newton's work, I think it is a significant fraction of that time period. And we need to ready our students because science and technology is advancing so rapidly. Exponentially is one way of describing it, but it is absolutely necessary to ready our students to apply modern methods which are pushed, not only developments in theory, but also experiments. Experiments are requiring more and more sophisticated theory for their understanding. And that's what physics is about, which is to understand nature.
So thank you.
So,
I think I have, as a follow-up question to this is this. As a teacher, when you go and you have to work out things on the blackboard, how do you really maintain a balance between the mathematical rigor which you share with your students and the physical intuition which you would like to convey to them? Because many a times, if you talk to a student, then he will say it is too rigorous a mathematics and maybe it is just beyond us. We would like to really feel it in terms of some physical intuition.
I think there is no way you can have a physical intuition for a vector in the Hilbert space. There is no simple way of doing it. You can give certain analogies like position vectors and so on. And as I think it was pointed out earlier also, you look at the coordinate representation or the momentum representation of these state vectors and then work with these representations. You have to get into mathematics. There is no escape from it. And I try to encourage my students to appreciate and enjoy the mathematics rather than considering it as an obstacle. I think it is not difficult. It is not very advanced mathematics. I think if you're teaching at an MSc, teaching an MSc course, of course, students have done differential equations in their BSc curriculum. But there is nothing beyond it in the Schrodinger equation. And of course, they have done matrix algebra in their mathematics courses earlier. So there is no reason to avoid it. And you get them to accept that, okay, this is something that you have done, enjoy it, rather than worry about it being too rigorous, too dry. On the contrary, I think it makes physics so beautiful. Like Dirac said that if you are humble, and I think this humility is really necessary. Means if you keep insisting that I must understand nature based on my experience of what I see, what I hear, what I touch, you cannot understand nature. Nature requires a different, you have to go beyond it. There is no way you can explain the Young's double slit experiment based on your experience, what you call as physical intuition. So you come to terms with it. That is where humility is required. That, okay, I will not understand it based on my personal physical experience. Let me think beyond it. The theory has been developed by stalwarts, Dirac, Heisenberg, Schrodinger, Niels Bohr, Max Born. It has been explained by these people. They have used mathematics. I have studied these mathematics in my BSc courses. What stops you from using it?
I think that's a great observation, sir. And for the benefit of our viewers here, I would like to read one very interesting comment which came on your book from Professor G. Bhaskaran of Mathematical Institute of Sciences, Chennai itself. Pranava, a well-known atomic physicist and a great teacher of quantum mechanics over decades, offers an excursion into the quantum world. He shares anecdotes, questions, solved problems, and insights in a non-traditional fashion. I would like to underline it, in a non-traditional fashion. One gets a glimpses of quantum mechanics. In excursion, some preparation and learning a little bit about the places of visit helps enormously. Similarly, a familiarity with quantum mechanics will help the students to appreciate the difficult subject presented in the book. I learned Feynman's path integral method somewhat late. It made a lot of sense and helped my research. Pranav's book thankfully introduces path integral method early in the beginning. His book is a Lego box. I think it's a wonderful analogy he makes about your book. With the precious pieces, students and teachers can build their own quantum world using the pieces. There is a lot to be gained from the book for hardworking students. Again, I would like to underline the term hardworking students. I think this is a very interesting and fascinating observation about book. I think he has summed up because he's a top researcher in condensed matter physics.
Yes.
And he has worked a lot on superconductivity, worked with P.W. Anderson also.
Yes.
I think if this observation is coming from him, I have, one very interesting thought which I would like to really think and, comment on it. Can you elaborate on how your book's pedagogical approach helps students transition from fundamentals to research level quantum mechanics? There is another observation which I made, by the way, let me mention that also, that you have been a great mentor with your students, not just within the classroom, but outside the classroom, by what you refer in your book as a fun quest. That's also a very interesting thing which you really mentioned there. So I would like you to elaborate on this aspect also for the benefit of the viewers, because already some questions are popping up in the chat box regarding how do we really take care of all these things at the undergraduate level. Thank you.
I think the answer lies in what Bhaskaran points out. If you want to learn quantum mechanics, or if you want to do physics, coming to think of it, if you want to do anything in life, even if you are to be an artist, you're playing tabla, there is no substitute to hard work. I was listening to an interview by Zakir Hussain, and he said कि हम दिन में 16 घंटे तबला बजाते थे. So there is absolutely no substitute to hard work. And I think if you're willing to put in that effort, I believe the book is very accessible, because it does not jump steps. But sometimes it is, if one is not used to it, you may have to read it a second time. And that's what hard work is about. I think it is a very accessible book. I don't think there is anything in that book which one cannot really find how it is developed. If there are major gaps, I would like to be pointed out, and I will try to bridge them if and when I have an opportunity. But having said that, most of my students over all these 4 decades that I have been teaching, they discovered for themselves that yes, it is, the contents are self-explanatory. All you have to do is that if it introduces new ideas, you need to open up your mind and again follow the mathematics. I think you will get a deep appreciation of the laws of nature, which is what physics is about.
Yes. So
You cannot explain why nature behaves the way she does. You can only try to describe nature for what she is and how these laws work. And that description requires a certain methodology. After all, it is the representation of the state of a system and how it evolves with time. Now, this requires operators. And these operators means you have the evolution is in terms of the Hamiltonian is in terms of the momentum operator, the momentum square. The momentum is a generator of translation in homogeneous space. So you get the gradient operator. How can you escape mathematics?
So may I summarize it by saying that there is no royal road to quantum mechanics.
Yeah.
One has to really traverse that path which one has to follow.
Yes. So I think I would encourage students and teachers to put in effort and enjoy the effort. If you have in our country in particular, we have a great tradition in mathematics and astronomy. I think we take great pride in it. We should use it to understand the laws of nature.
I think you have done a wonderful thing, which I would like to really say that very rarely, people will ever go to Feynman and Hibbs' book to study path integral approach. But now there is a book available right here with us, which can really introduce one to that approach and really do something and appreciate a very different perspective about how quantum mechanics is traditionally taught. Now, this also brings me to another very interesting aspect of your book, I was finding that it has a substantial introduction available to the students. And I think that should really encourage people to look at your book also on quantum computing and quantum information science. I think that's more than 125 pages introduction in your book itself. And we are talking so much about it. And here is an opportunity for us to think of bringing these things into the syllabus. And I would like to know from you, was this also one of the motivations that what role this can play in preparing students for research in the quantum computing or in quantum information science, or for preparing the quantum workforce for which we have now a huge quantum mission in place in the country itself?
I must submit that my book provides only the elementary introduction. It doesn't go too far, but it does provide elementary introduction and builds it on the basis of principles of quantum mechanics, which are discussed in earlier chapters. I mean, this whole idea of, I mean, what is central to quantum mechanics is this idea of probability. So these are fundamental ideas which one must appreciate, and they play a big role in understanding entanglement, which is, this transition from classical to quantum computing is no longer new. It was in the early 80s that this started. Means Feynman is always quoted for this, but not just Feynman. David Deutsch did the work around the same time. Benioff did the work around the same time, and these were. This is now more than 4 decades old, and it is impacting our life in a very big way. I mean, the technology is changing. The threats, the security threats are changing. And quantum computing has now become necessary, not just to guard ourselves from security threats, but also to solve problems for life sciences. You want to build a new drug, for example, you need quantum computing. So we need to introduce quantum computation, understand how entanglement gives you a tool to do computing, to answer your questions in a much more efficient way than what classical computing does.
Yes.
And this is exactly the idea that Feynman, Benioff promoted, that, okay, you can do things in a different way. And nature allows you, and these means you're not doing anything different. You're using the laws of nature. Nature is giving you these provisions.
But there is one thing more which I want to ask, maybe slightly off the book, is this that you are at the moment also developing some courses on NPTEL platform on quantum computing and maybe quantum information science. So how much of the training of what this book proposes is needed for those kinds of courses, because they are targeted to a very different audience, I believe, to the engineering students? Or is it for the undergraduate students studying in BSc also who can benefit from those courses?
Yes, these courses are for undergraduate engineering students primarily. And certainly I am drawing considerable material from my book, but also adapting it tailoring it to suit the build-up for this course. So I have to keep in mind the background of these students. And the main thing is that these students would not have taken a good number of physics courses, which our MSc physics students take. So MSc physics students, they also have done electromagnetic theory, for example. So the background in electrodynamics, wave theory, so these are not available to engineering students in their first or second year. So some of those ideas have to be explained in a slightly different way. And the material obviously has to be tailored and adapted. But I think a good bit of the core is what I'm drawing from my previous book.
Sir, you were present in the earlier session where we talked at length about the syllabi, etc. also. People have been talking about that some courses of this kind must be introduced at the undergraduate level so that they may get some job opportunities. In yesterday's interview also, Professor Ghatak was talking about, where are our students going to get jobs? And do you think that this kind of a small twist in tailoring the undergraduate curriculum will help a lot in, once again, as far as demand of physics students in the market is concerned, that get enhanced?
Yeah, I think the DST and AICTE have done a great job in this direction. And this is a part of the National Quantum Mission. As an integral part of the NQM, the DST and AICTE have come together to develop a curriculum, an undergraduate curriculum, which will be implemented in engineering courses for a minor degree in quantum technology. And they have invited a large number of experts from the country to come together to generate such a syllabus. I believe this syllabus is great, and we don't have to reinvent the wheel. This syllabus is going to be available to everybody. I think they are planning to introduce these courses from the very next semester after July or August. So it is just around the corner. And it is something which universities can adapt quite easily. They don't have to take it word by word. Each university can, make appropriate changes to suit its own structure. But I think I myself have some difficulty with this syllabus. I think some of the portions, if I were to have written it, I might have done it slightly differently. But I think that is a matter of individual approach. And that is still within about 5 to 10% at the most of what has already been done. And I think it's a great curriculum which has been developed by DST along with the ICTE. So I would suggest that should be the first reference point. And it is good enough, even if you just implement it as it is, I think it will be great.
And another supplementary question with it, let me come to, because IAPT is vertical is, very large. Schools we are talking about, and that how some kind of, such programs have been done by the IAPT itself, talking to the school students, and pilots have been done. I think very soon, maybe we will have a report of that kind also. What do you think that how school students can be encouraged to go beyond the what we call as the Bohr modern physics in the school curriculum, and talk about all these things, which encourages them to, that this is a great field in which one should come and opt for it beyond computer science itself.
Yeah, I think it is important to introduce these ideas even in the high school level. And things like the Gedanken experiments in Heisenberg microscope, for example. It is something which a high school student will be able to relate to. He doesn't have to do that experiment in a lab, but if you discuss it in the classroom, I think he comes to terms with the fact that it is not possible to measure position and momentum simultaneously. He certainly knows Newton's equation, F equal to dP by dt. And to solve it, he knows that you need the position and momentum at the t equal to 0. And if these are not measurable, you need a different theory. And he certainly should be introduced to this alternative theory, to which we have found no exception for 100 years. So I think it
Do
is
you think,
important.
sir, that there is something of this kind, that effort is being done to bring these at the school level also, maybe at the NCERT or CBSE level? Are there some kind of thoughts going on there also about it?
I believe these things are happening. Under the NEP, the NCERT is revising the curriculum for all the classes. From what I hear from my friends, they are doing it in various stages. They have done up to 5th, 6th, 7th grade, and there will be additional changes in the curriculum for the 9th, 10th, 11th, 12th grades. And I don't think that those things have been done as yet, but I believe they have identified some people who are working on this. There are very experienced and respected physicists on this task. And I am very confident that they will come up with an excellent curriculum.
So I think I would like to come to know another very interesting aspect, which maybe as a lay reader of a person who goes into a bookshop and wants to glance in your book will find it very exciting, is the wonderful, quotations and the anecdotes which you share in your book. Can you really let me and the viewers know that how you feel that these are very important elements of your text itself? And can you share one or two of your very favorite anecdotes which you have brought into the book? Uh, and you really love to talk about those anecdotes with the students whenever you are talking about this subject in the classroom.
Actually, there are fewer than what I would have liked. I think at the end of the day, as you pointed out, it is already more than 600 pages. And I had to leave out a lot of content. And what I ended up leaving out was a number of stories, sometimes which I enjoyed talking in the classroom. But over the years, I find that it is difficult to find time for these stories, no matter how exciting they are, because in a 40-hour course, if you want to begin at the beginning and then take them far enough, I think there isn't enough opportunity. So that's something which one can do once in a way. But I think we certainly hope that students have sufficient motivation to study quantum mechanics. Means I think if you want to be a physicist, how can you not have sufficient motivation? I think so to give them pep talks is not something which I think should be necessary. It is something to to take for granted that, okay, if you are in the business of becoming a physicist, then this is like basic training. Means it's आप संगीतकार होना चाहते हैं और आपको सारे गामा पढ़ना नहीं है तो कैसे चलेगा?
So I
So
think uh, I wish we had more time, and we are at the end of our interaction session, and I must thank you from core of my heart for sharing your insights with us today. And I think it should inspire not only students, but the teachers who are sitting in this particular program, that how these were, I think, when we were planning this program, we were thinking to bring case studies of authors, well established authors, to the audience, that how they work, how the mind of an author works, how they really bring things out, why they are so concerned about it. And that, I think, came out very nicely in your interview and in Professor Ghat's interview also. And I think the way Professor Bhaskaran has put your book in a very interesting perspective that should inspire us to go into this book and uh, follow it, and maybe make use of it in a very interesting fashion itself. And I would love that at least our teachers should take care of the wonderful new ways of looking at introducing uh, things in the curriculum itself. So thank you very, very much. Yes, sir. If you want to make some
yeah, I
remarks.
will like to make one small point.
Yes, sir.
I think every physicist, regardless of his interest being in theoretical physics or experimental physics, must know basic physics. A theoretical physicist should also be able to do optics experiments, interferometer experiments. Okay. I think it is expected that he is able to do basic experiments, enjoys it. And every experimentalist also knows basic theoretical truths. I will like to quote from a preface of a book which I had. It is, I think it is a book by Taylor, in which he writes in the preface that the book is written for experimentalists.
Yes.
Who are going to dirty their hands with grease and vacuum pumps and so on.
E.L. Taylor's book it is.
Yes. And he says that, okay, they need to know second quantization, elementary excitations in solids, phonons, and, superconductivity and so on. So and this is not a new book. It is a very old book. This is like 40-year-old book. And how much physics has advanced now?
Yes. Agree.
So I think both theoretical as well as experimental physicists must enjoy doing basic experiments in the labs, and also use basic theoretical thing. I mean, the kind of quantum mechanics that is there in these books, it's not very advanced. It's just differential calculus and matrix algebra. Nothing
Yes.
beyond it.
Sir, there is one remark in the chat box, and it says that we teach physical significance with contemporary examples at UG level to kindle interest in young minds. How will you really look at this? And the students are losing interest, and it is becoming difficult to draw them towards physics, application-oriented approach itself. Would you like to comment on this remark itself? This is by Dr. Sarla.
I think we have to explain to the students that, okay, all these physical ideas, they have certain limitations. And if you try to understand an electron spin in terms of rotation of a top, do you want to mislead them by giving an example which they have played with, or tell them the truth? That is a choice you have to make.
But sometimes, teachers have to draw analogies around, and they say, okay, there is no other way. We may have to really make use of such analogies. Maybe then we can slowly make a transition towards what spin actually is
Yeah,
in
so
quantum mechanics.
so sure enough, you can use these analogies, and these analogies were, in fact, they played a big role in the development of quantum mechanics, even in the ideas of the development of spin itself. And then Uhlenbeck and Gaudsmit, they ended up saying that it is all abracadabra. It was just like magic. But physics is not magic. It is, quantum mechanics is a theory.
So thank you very much, sir. I think now maybe we should have some comments and the questions if there are any from the audience. I think we would love to hear from our viewers here who have been with us all through this whole interview. So it's open for discussion now. Please come forward to share your thoughts on this particular session and the idea of these two book talks which we had here. Maybe Professor Ghatak, may I invite you to please share your thoughts with us on what we have gone through in today's interview.
No, but the only thing that I can say is, Professor Aliwalia, this is from the core of my heart. I want to congratulate you. You have put in really, I mean, of course, Professor Deshmukh also has to be congratulated, but I want to congratulate you for your relentless efforts in making physics meaningful. And I have been telling this to all of my friends that sometimes they say that I have not become a member of IAPT. I said you should become a member of IAPT today, because the way Professor Ahluwalia is making effort in promoting physics and things like that. So I really enjoyed this session. Both the Pruthul Desai's great talk. But let me tell you this thing. With all, I mean, Pruthul Desai, I am very, very fond of him. I have visited his college and I really like him. He is also a very dedicated teacher. And but it's a difficult lecture that he took upon his shoulders. It is a difficult lecture, so it's a very difficult lecture, and so therefore, what I am pained about is the fact that there are right now only in a country of 1.3 billion people, only 40 participants today. So let me be very frank. This pains me. Why is it so? And I don't know. There are many good, very outstanding physics teachers, and Professor Deshmukh, I mean, these two books have been really it's a different perspective. Even if I may not like to his rigorous perspective, but it's a beautiful perspective. And he has his own rules. People should be interested to listen. At least teachers should be able to listen. And I think, what is your membership number? 5,000, I think. In thousands,
I think 10,000 now.
10,000.
Yes.
So, देखिए 10,000 में से 40 on a, maybe because it is today is a Saturday afternoon. I don't know, but
one saving grace which I always see in this, and we were discussing this also. So we are thinking of making reels which people actually look at on Instagram.
Say that again. I couldn't follow that. Say that again, please.
Yeah. What I'm saying is that these days technology offers us some very interesting ways, like converting these sessions into small reels or those very interesting points which have been made, and then try to take them to the audience.
Yes,
The
that,
website has got that kind of an opportunity actually.
yeah. And this is
And
this,
YouTube, channel is there of ours, and we are, making all out effort to propagate that. Look, here is a YouTube channel. A lot of resources are being generated. For example, in these 3 months, we have generated a resource of about 18 hours. That's a very, very important
yeah.
thing which has happened.
So another thing that has happened is there is an information explosion. There is too much available on the internet. आदमी के पास time भी तो finite है, limited है. And even at this age, my time is limited. Uh, my family wants to have dinner, and so we have to compromise here and there and things like that. So there are problems. And particularly with the younger generation who have children to look after, young teachers or young these things. So
you'll be happy to report one thing.
one of the things that worries me is how to motivate the young teachers to physics. Physics teachers, they are teaching physics. They should be motivated in physics, but they are not. They are not, and that is reflected on the number of people who are attending today's event and things like that.
So there is one thing which I would mention, that in the last 2.5 years, how many emails we must have sent to our members? 3 lakh emails we have sent to our members. Every time when we send a notice to our members, it is sent to 4,000 people in one go. And we can see who are opening, who are clicking, and that kind of a analytics is available to us. So I think only because of that, we are having I would say, not a very disappointing hit rate, but it's reasonably good.
No, you're at. No, really, I'm not telling you because you're in front of me or because you had me yesterday, but really, it's a tremendous effort. But there is also a time limitation of the participant. Even, let me be very frank. Sometimes WhatsApp messages I just am unable to open because there is so many WhatsApp messages that come to me, including criticism or appreciation of my books to some old friend or relative or something like that. It's just enormous explosion of information, and so I would like both of you to share with me and others, if necessary, the syllabi that Professor Deshmukh mentioned that has come up in the NCRT NEP or something like that, the school level syllabus which introduces quantum theory. I would like to see that, and how we have to first train the teachers. That is very important, to train the teachers, and if IAPT can take some role with the help of NCRT, I don't know. But I have thoroughly enjoyed this session, both the lectures, both your discussion and your efforts. I really admire Professor Ahluwalia. I congratulate you and also Professor Deshmukh and Professor Pruthul Desai. So let others speak. I have been talking a lot.
Yes, sir. Please raise your hand and ask your, or if you want to give some comment or remark. Yeah, Rutika Rawat, please come on, ask.
Yes, sir. My question is to Professor Deshmukh, sir, and question is regarding Born-Oppenheimer approximation. So my question is that in that approximation, there is there is a point that we have to neglect the interaction between rotational and vibrational energies. So my question is, if we can consider that interaction, so could we extract any new information about that molecule, like that we have extracted a moment of inertia and bond length, when we have considered pure rotation and pure vibration?
Certainly, yes. In fact, I will have to dig out some references, but perturbative treatment of this rotational vibrational interactions has been studied quite some time back. I remember to have read a paper on this several decades ago, and I have not followed up the literature, but many of these things lead to consequences which are observed in experiments. So the short answer is yes. I will be happy to get you some references in this.
Thank you, sir.
Anybody else, please?
Priyamvada.
Priyamvada. Priyamvada, please.
Yes, sir. Good evening, sir. My question is to Professor Deshmukh, sir. And I am a undergraduate student and studying quantum or basics of quantum theory itself for me has been a bit difficult comparing to classical physics, as it is just now that we are slowly getting into the quantum realm. And I want to ask whether there's any way that we can visualize quantum physics in a way that we visualize classical physics. Just for example, how we visualize any gravitational forces or frictional forces in classical physics. Is there any way to visualize quantum physics so that a person who's just now getting into it can understand?
My very humble take on this is that quantum mechanics is very easy to understand if you stop making an effort to visualize it. If you insist on understanding it in terms of what you can visualize, you will keep running into difficulties. I think you need to stop making an effort to understand it in terms of what is visualizable. You need to understand the theory, but then you must, I will like to quote Dirac in this, that as you build the theory further, beginning with its ansatz, then it tells you how to connect it to observations, which is what you will visualize. You see the spectral lines, for example. You have seen the sodium vapor lamp. You have seen the D1, D2 lines. That is visualization. And to understand those intensities, quantum mechanics is the only way you can get those intensities right. So visualization is possible at that level once you build the theory further. But for that, you need to understand what are transition matrix elements. You need to understand the Wigner-Riccard theorem. Get there. Then you can visualize it. If you try to visualize a wave function, it's not going to happen. So quantum theory is about observations. The whole theory is aimed at understanding what you observe. But that doesn't mean that the vector in the Hilbert space is observable. You can construct other entities using these vectors, which are visualizable. So try to visualize what is visualizable, but you have to get there. That's not going to happen at the level of just looking at a vector in the Hilbert space. You have to go beyond it.
So I think, sir, we can stop.
Professor Ahluwalia, can I make a small comment?
Yes, sir.
This is related to the answer to, I will respond to the question raised by Miss Priyamvada. Yeah. So what Professor Deshmukh mentioned is absolutely right. Absolutely right. However, what I would like to request Ms. Priyamvada is that you listen to the Feynman's 6th lecture in the Messenger series, and in which, as Professor Deshmukh himself mentioned, that the two-slit experiment, this will help visualize the peculiarities of quantum theory. And he so beautifully explains that two-slit interference experiment with single electrons or single photons or single proton. And that lecture without using complicated mathematics allows you to visualize the complexity of quantum mechanics and the way we would like to understand and quantum mechanics, and that an electron, and that's what Dirac also mentions, an electron or a photon interferes with itself to create a probability distribution, and it is that probability distribution that results in the interference pattern. So some of the concepts, Professor Deshmukh is absolutely right that you have to go to the mathematics to understand the basic concepts in quantum mechanics. At the same time, understanding the two-slit experiment, as beautifully explained by Feynman in his 6th lecture, and also in his famous Feynman lectures, also allows you to visualize that on a not, I would say, qualitative level. It is a quantitative level, but without going into the depth of algebra. This is my observation.
Thank you very much, sir.
Thank
Ms.
you.
Priyambada, could I make something clear to you or something like? Listen to that Feynman lecture from the full Feynman lecture. You will enjoy it.
Yes, sir. Thank you.
It is on YouTube.
Thank you
It is
so
on
much.
YouTube. You go to YouTube and write Feynman's messenger lecture on probability and uncertainty. It's a beautiful exposition of basic concepts in quantum theory.
Yes,
So
sir.
thank you once
absolutely
again,
look
Professor
into
Ghatak,
and
Professor
you
Deshmukh,
very
and
much.
Professor Pruthul, and Professor Madhusudan, back to you.
Thank you, sir. As Professor Aluvala sir rightly pointed out, IIPT RC22 thanks both the speakers, Professor Pruthul sir and Professor PC Deshmukh sir, for their time and giving their lectures and also interacting with all the participants and young students like Priyamvada, and IIPT feels very much grateful to both the speakers. And tomorrow we have 2 more sessions by Professor S.W. Anwane on Dirac picture, and IIPT National President Professor Aluvalis are speaking on some applications of quantum mechanics. With these few words, if there are no questions, again we thank both the speakers and let us wind up this session. Shall I, sir? Aluvalis sir?
Yeah, thank you very much. I think we can sign off now. Once again, thank you, Professor Deshmukh and Professor Ghatak and Priyambada and Rutika. I think you too has made this session very interesting. Your presence has been great.
Thank you.
Thank you, sir.
Thank you
Thank
all.
you, sir.
I'm signing. Let us sign off. See you tomorrow.